Venus holds a unique position in our solar system as the second planet from the Sun, with its distance from our star playing a crucial role in determining its physical characteristics, climate conditions, and observational properties. This planet's orbital parameters and position relative to the Sun have significant implications for its evolution and current state, making it one of the most fascinating celestial bodies to study in our cosmic neighborhood. Venus orbits the Sun at an average distance of 67 million miles, 108 million kilometers. This measurement is commonly expressed in astronomical units, AU, with Venus positioned at approximately 0.723 AU from the Sun. One astronomical unit represents the average distance between Earth and the Sun, about 149.6 million kilometers, making Venus's orbit about 72.3% of Earth's distance from the Sun. This positioning places Venus between Mercury and Earth, contributing to its status as Earth's closest planetary neighbor at certain points in its orbit. The precise orbital parameters of Venus include a semi-major axis of 0.723 AU, 108,200,000 kilometers, 67,200,000 miles. This measurement represents the average of the planet's closest and farthest distances from the Sun throughout its orbit. The semi-major axis serves as the primary metric for describing a planet's position relative to the Sun and is a fundamental parameter in calculating other orbital characteristics such as period and velocity. Venus's proximity to the Sun results in it receiving approximately 1.9 times more solar radiation than Earth. This intensified solar input contributes significantly to the extreme surface conditions found on the planet, where temperatures can reach approximately 900 degrees F, 482 degrees C. This makes Venus hot enough to melt lead and the hottest place in the solar system aside from the Sun itself. The relationship between distance from the Sun and surface temperature is dramatically illustrated in Venus's case, demonstrating how planetary positioning can influence environmental conditions. One of Venus's most remarkable orbital characteristics is its exceptional circularity. While all planetary orbits are elliptical to some degree, Venus's orbit deviates minimally from a perfect circle. The planet has an orbital eccentricity of just 0.007, which is extraordinarily low compared to other planets in our solar system. This eccentricity value indicates how much an orbit deviates from a perfect circle, with 0 representing a perfect circle and values approaching 1 indicating increasingly elongated ellipses. This minimal eccentricity gives Venus the distinction of having the least variation in distance between its closest approach to the Sun, perihelion, and its farthest point, aphelion, of any planet in our solar system. The difference between these two extremes amounts to only about 1.46 million kilometers. To put this in perspective, Earth's orbital eccentricity of approximately 0.07 results in a distance variation of roughly 5 million kilometers between perihelion and aphelion. For Venus, the nearly constant distance from the Sun creates relatively uniform conditions throughout its orbital period. The exceptional circularity of Venus's orbit stands in stark contrast to those of other planets like Mercury, with an eccentricity of 0.206, or Mars, 0.093, whose distances from the Sun vary significantly more throughout their orbits. Among all planets, Venus possesses the orbit closest to a perfect circle, with its eccentricity of less than 0.01. This orbital characteristic is one of the defining features of Venus and has important implications for the planet's climate stability and temperature uniformity across its surface. The time required for Venus to complete one full circuit around the Sun is approximately 224.65 Earth days. This means that a Venusian year is shorter than an Earth year, but significantly longer than Mercury's 88-day orbit. During this period, Venus travels a distance of about 4.54 astronomical units, 679 million kilometers or 422 million miles, in its journey around the Sun. This substantial distance covered in a relatively short time results from Venus's relatively high orbital velocity. Venus moves through space at an average orbital speed of approximately 35 kilometers per second, 78,000 miles per hour. This velocity is greater than Earth's orbital speed of about 29.8 kilometers per second, consistent with Venus's closer position to the Sun. According to Kepler's laws of planetary motion, objects closer to the Sun orbit at greater speeds than those farther away, explaining why Venus travels faster through space than Earth, despite having a shorter total orbital path. An interesting relationship exists between Venus's orbital period and Earth's. After 5 synodic periods of Venus, the time between successive alignments of Venus, Earth, and the Sun, Venus and Earth return to nearly the same relative positions. This cycle, lasting about 8 Earth years, means that Venus appears in almost the same position in Earth's sky every 8 years, creating a predictable pattern that has been recognized since ancient times. Venus exhibits a fascinating relationship between its orbital and rotational periods. Unlike most planets that rotate in the same direction as their orbital motion, Venus rotates in a retrograde direction, clockwise when viewed from above the Sun's north pole. This means that on Venus, the Sun rises in the west and sets in the east, the opposite of what occurs on Earth. Even more remarkably, Venus takes approximately 243 Earth days to complete one rotation on its axis, longer than its year of 224.7 Earth days. This makes Venus the only planet in our solar system where a day is longer than its year. This slow rotation is believed to be the result of a complex interplay between gravitational tides caused by the Sun and atmospheric tides generated by solar heating of Venus's thick atmosphere. The planet's proximity to the Sun enhances these tidal effects, contributing to its unusual rotational characteristics. The current rotation period of Venus represents a state of equilibrium between these competing forces. Scientists believe that Venus did not always rotate as it does now. When the planet first formed, it likely had a different obliquity and rotation period. Over time, the combination of tidal effects and planetary perturbations gradually altered its rotation to the current state, illustrating how a planet's distance from its star can influence its rotational evolution through gravitational interactions. While Venus's distance from the Sun remains relatively constant, its distance from Earth varies dramatically throughout its orbit. When Venus is at inferior conjunction, passing between Earth and the Sun, it approaches within approximately 42 million kilometers of our planet. At superior conjunction, when Venus is on the opposite side of the Sun from Earth, the distance increases to about 258 million kilometers. This substantial variation in distance affects how Venus appears from Earth and has important implications for space mission planning. The average period between successive conjunctions of the same type is 584 days, which represents one synodic period of Venus. This cycle determines how frequently Venus transitions from being a morning star to an evening star in Earth's sky. The synodic period is longer than Venus's sidereal orbital period, because Earth is also moving around the Sun during this time, requiring Venus to catch up to reach the same relative position. In the current era, the closest that Venus comes to Earth is just under 40 million kilometers. This minimum distance changes over long time periods due to the evolution of both planets' orbital eccentricities. Historical data indicates that the last time Venus came closer than 39.5 million kilometers to Earth was in 1623, but such a close approach will not occur again for many millennia. In fact, after the year 5683, Venus will not come closer than 40 million kilometers to Earth for approximately 60,000 years, demonstrating how orbital parameters slowly evolve over astronomical timescales. Venus's position relative to the Sun and Earth occasionally results in a rare and scientifically valuable phenomenon known as a transit. During a transit, Venus passes directly between Earth and the Sun, appearing as a small black disk moving across the Sun's face. These events are rare because Venus's orbital plane is inclined at 3.4 degrees to Earth's orbital plane. This inclination means that Venus usually passes either above or below the Sun, as seen from Earth during inferior conjunction. Transits of Venus occur in pairs separated by 8 years, with pairs separated by more than a century. The last pair of Venus transits occurred in June 2004 and June 2012, and the next pair will not occur until December 2117 and December 2125. These rare events have historical significance in astronomy, as they were used in the 18th and 19th centuries to help determine the scale of the solar system and calculate the astronomical unit more precisely. A remarkable mathematical relationship exists in the orbital periods. 5 synodic periods of Venus almost exactly equal 13 Venusian years and 8 Earth years. This coincidence means that the relative positions of Venus, Earth, and the Sun nearly repeat after this cycle, creating predictable patterns in Venus's appearances from Earth. This cyclical relationship was recognized by ancient astronomers and featured prominently in some ancient calendrical systems, particularly those of Mesoamerican civilizations like the Maya, who carefully tracked Venus's appearances and disappearances. Venus's distance from the Sun directly influences its appearance from Earth, giving rise to its prominence in various cultural and historical contexts. As the brightest object in the night sky after the Moon, Venus has captured human attention since prehistoric times. Its brightness results from a combination of its relatively close proximity to both the Sun and Earth, and its highly reflective cloud cover that bounces back about 75% of the sunlight it receives. In Roman mythology, Venus was identified with the goddess of love and beauty, Aphrodite. This association likely stems from the planet's brilliant appearance in the sky. However, not all cultures viewed Venus in such a benevolent light. To the ancient Mayans, Venus was associated with warfare and was called Kukulkan, or the feathered serpent. The Mayans developed elaborate calendars to track Venus's movements, which were directly related to its distance from the Sun, and the resulting visual cycle as seen from Earth. The consistent brightness of Venus, determined by its distance from the Sun, has made it an important navigational aid throughout human history. Sailors and travelers have used Venus as a reference point, particularly during twilight hours when the planet is most visible. This practical application underscores how Venus's orbital position has influenced human activities and cultural developments throughout history. Venus's distance from the Sun creates specific challenges and opportunities for space exploration. Being closer to Earth than Mars or the outer planets, Venus requires less travel time for spacecraft, making it an attractive target for early planetary exploration. However, the planet's proximity to the Sun means that spacecraft visiting Venus must contend with much higher levels of solar radiation than at Earth, necessitating additional thermal protection. The journey to Venus can be completed in as little as 3 to 4 months using conventional propulsion systems, compared to the 6 to 9 months typically required to reach Mars. This relatively short travel duration made Venus a frequent target for early interplanetary missions, with the Soviet Venera program and NASA's Mariner missions pioneering exploration of the planet in the 1960s and 1970s. More recently, Venus has been used as a gravitational assist target for spacecraft heading to other destinations in the solar system. The Parker Solar Probe, for example, is using multiple Venus flybys to gradually adjust its orbit to achieve unprecedented close approaches to the Sun. During these maneuvers, the spacecraft uses Venus's gravity to alter its speed and direction. In November 2024, NASA's Parker Solar Probe performed its final flyby of Venus, which set it on a trajectory to pass within an unprecedented 3.86 million miles of the solar surface on December 24, 2024. This demonstrates how Venus's position in the solar system makes it useful for gravitational slingshot techniques. The proximity of Venus to the Sun also affects communications with spacecraft in Venusian orbit or on its surface. When Venus is on the opposite side of the Sun from Earth at superior conjunction, radio communications can be disrupted by solar interference. Mission planners must account for these periodic communication blackouts, which are a direct consequence of the geometrical arrangement of Venus, the Sun, and Earth. During the Parker Solar Probe's close approach to the Sun in December 2024, NASA Mission Control anticipated being unable to contact the spacecraft for approximately 3 days due to such interference. The distance between Venus and the Sun is fundamentally governed by gravitational forces. The Sun, containing about 99.86% of the mass in our solar system, exerts a dominant gravitational pull on all planets, including Venus. According to Newton's law of universal gravitation, this force is proportional to the product of the masses and inversely proportional to the square of the distance between them. For Venus, with its mass of about 4.871024 kilo orbiting the Sun, 1.99 x10 or 30 kilo, this relationship maintains the planet in its stable orbit at an average distance of 108 million kilometers. While the Sun's gravity is the primary force determining Venus's orbit, the planet also experiences smaller gravitational perturbations from other bodies in the solar system, particularly Jupiter, the most massive planet, and Earth, its closest planetary neighbor. These additional gravitational influences cause minor variations in Venus's orbital parameters over time. However, due to the relative isolation of the inner planets from the massive outer planets, Venus's orbit remains remarkably stable over long time periods. The relationship between gravitational force and orbital distance follows Kepler's third law of planetary motion, which states that the square of a planet's orbital period is proportional to the cube of its semi-major axis. This law explains why Venus, at 0.723 AU from the Sun, completes an orbit in 224.7 days, while Earth at 1 AU takes 365.25 days. The mathematical relationship between these values confirms the fundamental physical principles governing planetary motion. Venus's nearly circular orbit suggests that it has reached a highly stable configuration in its dance around the Sun. Computer simulations of solar system evolution indicate that the current arrangement of planets represents a stable solution that has persisted for billions of years. The gravitational interactions between the Sun, Venus, and other planets have settled into this configuration through a process of dynamic evolution since the solar system's formation approximately 4.6 billion years ago. Venus's distance from the Sun directly influences how we observe it from Earth. Being an inferior planet, Venus never appears far from the Sun in our sky. The maximum angular separation between Venus and the Sun, as seen from Earth, known as greatest elongation, is approximately 47 degrees. This means that Venus is visible either in the western sky after sunset or in the eastern sky before sunrise, but never in the middle of the night, when the Sun is on the opposite side of Earth. After the Sun and Moon, Venus is the brightest object in the sky, capable of casting shadows on Earth under ideal conditions and sometimes visible even in daylight. This exceptional brightness results from a combination of factors related to Venus's distance. Its proximity to the Sun provides abundant illumination, while its relatively close approaches to Earth during portions of its orbit make it appear larger. Additionally, Venus's thick cloud cover reflects about 75% of the sunlight that reaches the planet, giving it an exceptionally high albedo. Venus reaches its maximum brightness when it is at a phase of about 25% illuminated as seen from Earth. At this point, the combination of its relatively close distance to Earth and the visible portion of its sunlit face creates the optimal conditions for brightness. During these periods of maximum brilliance, Venus appears as a strikingly bright star in the morning or evening sky, earning it the names morning star and evening star in different cultural and historical contexts. Venus's distance from the Sun fundamentally shapes nearly every aspect of the planet, from its physical properties and climate to its appearance in Earth's sky and the challenges of exploring it with spacecraft. Positioned at an average distance of 67 million miles, or 0.723 astronomical units from our star, Venus occupies a unique place in the solar system that has influenced its evolution and current state. The nearly circular orbit of Venus, with its remarkably low eccentricity of 0.007, results in minimal variation in its distance from the Sun throughout its 224.7-day year. This orbital stability contributes to the extreme uniformity of conditions across the Venusian surface, where temperatures remain consistently hot enough to melt lead due to a runaway greenhouse effect enhanced by the planet's proximity to the Sun. Venus's position as the second planet from the Sun also determines its relationship with Earth, creating patterns of close approaches and conjunctions that have fascinated astronomers since ancient times. As our nearest planetary neighbor at times, Venus has played a crucial role in the development of astronomical measurement techniques and our understanding of the solar system's scale. The ongoing exploration of Venus by spacecraft continues to refine our knowledge of its orbit and distance from the Sun. The Parker Solar Probe's use of Venus for gravitational assists demonstrates the practical applications of understanding Venus's position in the solar system. Future missions will undoubtedly provide even more precise measurements and insights into how Venus's orbital characteristics have influenced its past and present conditions, potentially offering clues about the divergent evolutionary paths of Earth and its sister planet. Understanding Venus's distance from the Sun provides valuable context for comparative planetology, helping scientists unravel the complex processes that shape planetary systems, both in our solar neighborhood and beyond. As we continue to discover and characterize exoplanetary systems around other stars, the example of Venus serves as an important reference point, illustrating how a planet's distance from its star profoundly influences its destiny.